And then he moved to the IES, where he continued his work on spinning dust. And now he also works on neutrino physics, large-scale structure a little bit, and he's going to talk about exactly those topics today. Well, at least about large-scale structure and recombination also.
No, but it's okay.
All right.
Thank you. Thank you, Dan. So, thank you for having me and for the 30% of the audience who already saw my talk yesterday. There will be some overlap, but I won't have to speed this time. So this is the outline. If I have managed to go through everything, I will first talk about work with Julian Munoz, who's a graduate student of Mark Minkowski at Hopkins, on primordial non-Gaussianity and how we can extract it from the 21 centimeter bispectrum. And in particular, I will mention that the secondary non-Gaussianities are really large. I will briefly talk about some work in progress, which is on how accurate is the actual standard expression for the gravitational bispectrum. And on the second part of the talk, I will talk about how to probe dark matter baryon or dark matter photon interactions within the early universe, either with 21 centimeter fluctuations. This is also work in preparation with Julian Munoz, Eli Kovets, and Mark. And also, I'll talk about how one can already set some constraints on dark matter baryon and dark matter photon interactions with spectral distortions. And this is with Jens, who is the spectral distortion expert, as some of you might know, and Mark. So let's start with the bispectrum of 21 centimeter fluctuations in the dark ages. So, as you all know, the CMB temperature and polarization anisotropies are exponentially damped beyond the Silk damping scale, which corresponds to wave number of about 0.1, 0.2 inverse megaparsecs, L of about 2,000 or so. Large-scale structure surveys are limited by a different issue, which is the fact that things are nonlinear beyond k of 0.1 or so, and then if you like effective field theory, you can go to 0.3, but you can't go much beyond this scale. However, 21 centimeter fluctuations are in principle, only limited by the gene scale, which is at wave number of 300 inverse megaparsec. And you can also do tomography. CMB has only one surface of last scattering, but with 21 centimeter, you can have a whole three-dimensional map of the universe. So in principle, you have a huge number of modes available. We will focus, on this talk, I'll focus at redshift greater than 30, because then we can assume that the signal is rather clean. There are no luminous sources, so it's in principle very simple. The power spectrum, you can already measure a bunch of things. This was first pointed out by Lopez Ardarega in 2004. Dan and I worked on showing that you could also measure the very small scale power spectrum, even if you didn't have the angular resolution, because through the relative velocity effect, there's some impact on the large scale power spectrum. And finally, so what I will talk about here is that potentially with all these modes, 21 centimeter could be a game changer for primordial non-Gaussianity. You could measure FNL, the non-Gaussianity parameter, to exquisite accuracy in principle. So there are many challenges. This is why I keep saying in principle. First of all, the system temperature, so just the thermal noise in your receiver, is really huge because you have synchrotron radiation that increases at lower frequencies. That will be probably one of the biggest challenges. Foregrounds, which are already a challenge, as some of you know, even for lower redshift 21 centimeter, is going to be even worse for redshift 30 or so. The sheer volume of the data and how to extract a bispectrum. This is already difficult for a CMB. It's going to be even worse if you have a three-dimensional map, etc. But these are all details. What I will focus on is another challenge, which is much more manageable, is the secondary non-Gaussianity. So if you just took a bispectrum of the data, you would not get just the primordial bispectrum which you're after. So to compare with the CMB, in the case of the CMB, the secondaries are dominated by the ISW lensing correlation. So the same large-scale structure that lenses the CMB also produces the integrated Sachs-Wolf effect. So the statistical error on the FNL parameter from the CMB is about 5, and the bias due to the secondary is also about 5. Okay, so if you manage to model the secondary to 10% accuracy, you can subtract it, and you're not going to increase your noise by very much. Now, what are the secondaries for the bispectrum of 21 centimeters? So of course, you also have this ISW lensing, and on large scales, there are probably other effects that matter, but I'm going to focus on the small scales. So there are two major secondaries. First of all, the density field is nonlinear because of gravitational collapse. So you have a linear density field, delta, which I call delta 1, and then you have the second order density field, which is related to this kernel, this famous kernel, 5/7, blah, blah, blah. And I'll talk about this in the next part of the talk. So it's related to the linear density field. So basically delta, I'm going to write it, so delta is like delta linear plus something that's of order delta linear squared. The second reason why you get secondary is that the brightness temperature itself is intrinsically a nonlinear tracer of the density. So this is the formula for the brightness temperature. So really the brightness temperature contrasts with the CMB. So this is the optical depth, the mean optical depth that you multiply times 1 plus the density, because this is the local optical depth. It depends on the local density. In the denominator, you have a velocity gradient, which changes the local value of the Hubble expansion rate, which changes the escape probability of 21 centimeter photons. The spin temperature depends on the gas temperature and the gas density, because collisional rates, the competition between collisions and CMB photon absorption and emission set the spin temperature. So you see that this whole thing, and finally the gas temperature itself is close to the CMB temperature at high redshift, but at redshift less than 200 or so, which is why you can start to observe the 21 centimeter signal, it will tend to behave to cool down adiabatically and go as the gas temperature to 2/3. So all this to say that the 21 centimeter brightness temperature, though you can compute it from first principle, it's not difficult to do so in the dark ages, but it depends in some complicated way, in some nonlinear way, on the local density. All right, so yes, you're absolutely right. Yes, yeah, there is some. This depends. Yes, you're right on the spin temperature too. Yeah. So in both cases, the 21 centimeter brightness temperature fluctuation is some coefficient times the local linear gas density or baryon density plus some other coefficient of the same order of magnitude times delta squared. All right. So order of magnitude of the bispectra, the secondary bispectrum, so coming just from these nonlinearities, you take 3 delta T21. Okay, so you're going to get from two of them, you take this term, and for the third one, you take this term. So this is the order of magnitude. It's delta, delta, delta squared. So you get something like delta to the 4th. Compare this to the primordial bispectrum. So you just take three of these linear terms, but one of these deltas, you rewrite it as delta is delta Gaussian times 1 plus FNL phi, where phi is the primordial potential. So this is what I did here. So then this primordial bispectrum is going to be of order 3 deltas FNL phi. Okay, so it's FNL delta cube phi. So the ratio is of order FNL times phi primordial over delta. Phi primordial is a few times 10 minus 5. Delta, if I look at, say, k of 0.1 inverse megaparsecs, which is the nonlinear scale today. So at that scale today, delta is 1. At redshift 100, it's about 10 minus 2, which is why I get this estimate. So the primordial bispectrum is for FNL of 1, which is, really what we would like to detect, but we would like to detect even less than that, is at least 1,000 times less than the secondary bispectrum. Okay, so this is the actual calculation. Julian went to great care to actually compute these bispectra. This is the the bispectrum in equilateral triangle as a function of the multiple moment L, the secondary bispectrum, and then the primordial bispectrum for different shapes of the primordial non-Gaussianity, either the local type, equilateral type, or orthogonal type. And all this is for FNL of 1. So you see that there are 2 orders of magnitude difference, up 2 to 3. And same thing, this is the bispectrum in the squeeze limit, when one of the L's is 1/50 of the others. So you might say, okay, this bispectra, the secondary bispectrum is large, but it may have a very different shape, so then it shouldn't be a problem. It turns out, and that was a surprise to us, that if you defined a scalar product, so this scalar product is basically the sum over all L's of all the triangles of the 2 bispectra divided by the noise, so divided by 3 CLs. So this defines as scalar product. So if you ask what is the cosine of the angle between the primary and the secondary bispectra, this is typically between 0.8 and 0.9. So these two bispectra are actually very aligned. And the reason is that they're both very smooth functions of the wave number. So if you take very smooth functions, you can try it, take two power laws, different power laws, and you take their product, integrate, you will get some order unity alignment. So,
how about orthogonal? Because you would think that goes to 0, right?
Yeah, this is less, but it's still of the same order. Yeah. And this is for a single redshift slice. So you already have integrated, either if you do your flat sky approximation or if you do the full JL, you already have integrated. So
Right.
you smooth it already a little bit.
Yeah.
So if you go to an angular resolution corresponding to 0.1 arcminute, and you compute what would be the bias if you had a naive estimator for FNL, they would be biased because of the secondary bispectrum by of order 1,000 to several thousands. And again, we would like to get, so the CMB tells you that this number is less than 5, and we would like to get much better than the CMB. So this could be an issue. So even if you have a less 0.1% inaccuracy in your estimate of the secondary bispectrum, you would get a bias of order 1. So there are many things that are not accurate at 0.1%. For example, we don't know cosmological parameters today to 0.1%. So let's hope that we will know them to 0.1% by the time we put a telescope on the far side of the moon. For example, we don't know the detailed atomic physics of 21 centimeter transition to 0.1%. For example, if you look at this paper by Herat and Sigurdsson, they show that the spin temperature is really velocity dependent. And I'm sure there are more effects like this. So this is an exercise as a proof of principle, because again, in 30 years, who knows how we should marginalize over, what parameters we should marginalize over. But we have a marginalized over 4 parameters, which are essentially the derivative of brightness temperature with respect to the density, to the square of the density, to the velocity gradient, etc. And what we find is, so this is basically projecting the observed bispectrum on the space orthogonal to the secondary bispectra. Okay? And so what you do is that you reduce the signal to noise. And in this case, when you have 4 parameters, we reduce it by a factor of 5. It depends on the shape. If we had more parameters, we tried with like really marginalizing over 21. There are actually 21 different geometrical shapes. And you reduce it by a factor of 10 or something. So you do reduce it. But at the end of the day, if you co-add redshift slices and you enforce that these parameters have to be smooth functions of redshift, you will still get these incredibly optimistic results, as Dan said that they were very optimistic. You can still, in principle, measure FNL to very high accuracy with 21 centimeter. Okay, so if you had, again, an experiment that could go to 0.1 arcminute resolution, Richard is laughing, observe the whole sky. This is with the cosmic variance limit, no foregrounds, etc. And you had a 0.1 megahertz frequency resolution. That's probably not too hard. You can probably do better, I guess. But not cosmic variance limited, of course. You would get... Exactly. So this is an academic exercise, but we're among academics. But the take-home message is that we often think of the dark ages as this very simple universe. Well, there are actually very large intrinsic non-Gaussian to the signal, and they will have to be accounted for. They're not a showstopper, and many other things might be a showstopper. So you just have to know that there are intrinsic non-Gaussian and that have to be accounted for. All right.
Can you elaborate a bit more on why the shapes are aligned? So you said that any smooth function of k.
Right. So if you had, f of k is k to the alpha, and g of k is k to the beta, and I define fg as some integral from k min, and let's say this is minus alpha minus beta, to infinity of f times g dk. So you can do this exercise, and you will find that for alpha, very different from beta, the functions will be very aligned. For example,
the triangle shapes are these shapes are chosen to be somewhat orthogonal, I thought.
They're chosen to be in somewhat, sorry?
Somewhat orthogonal, right? So the orthogonal orthogonal template, I thought.
But they are orthogonal at the level in K-space at the level of the potential, but then you have the transfer functions, and then you have to integrate along one of the 3 K modes to get basically the L space by spectrum. So yeah, they're not perfectly aligned. I'm doing this in L space.
But you were saying though, I mean, the signal physically is 3D.
The signal is what?
You're still projecting those modes. Right?
But at the end of the day, by summing over different redshift slices, it's almost like doing it in K-space, and then it doesn't matter anymore.
So then why then again is it so overlapping?
But for a single redshift slice, it's very overlapping.
Oh, okay. So it's problems only if you look at a single redshift.
Yes. Yeah.
Oh.
Yeah. But it's still.
That's the case though, right?
Why wasn't it never the case?
Well, because the actual surveys will be looking over some finite redshift, right?
Do you not consider the correlations between all the redshift slices? Because you've got it's a 3-dimensional.
Right. But so I don't know how it's going to be done eventually. But so the way we did it is that at every slice we compute the bispectrum in L space at this slice, and then we co-add slices that are uncorrelated, that are far enough that they're uncorrelated. So we didn't do it as if it was a perfectly 3-dimensional volume, because it might not have the same properties, in the angular direction and the z direction. But again, I mean, these are kind of details. The main point was to say that there are large secondaries. That was the main point.
You have more information if you don't do that.
If you don't do what?
Have angular slices that are separated in redshift.
If you just do the 3-dimensional
Yeah,
power
if you
spectrum,
were to do the 3-dimensional.
it might be.
Is that realistic? Because isn't the point that the systematics might be different at every different frequency, and therefore every redshift slice?
Well, I don't know, but the power variance limited.
But I agree that this is a detail.
The assumption for all the 21st century analysis is that you can consider the correlation. Right. Otherwise, you're throwing away you're throwing away a lot of your signal.
You cannot what? Sorry.
The assumption is that you always consider the correlations between the redshift slices.
Yes.
Otherwise, you just throw away a lot of your signal.
I see.
Yeah, you throw away a lot, a reasonably large amount.
Okay.
You can get those numbers equal well.
So it helps you.
So.
So is it possible to use the redshift space distortion, to sort of back out some of these secondaries as well?
I haven't thought about this, but yeah, I don't know. I would imagine it would be just yet another secondary, if anything, but I don't know. Because it's not like redshift space distortions will only affect. I mean, it will affect the signal,
right.
the whole signal.
The primordial, bispectra that don't produce the particular pressure-like distortion, whereas these secondaries
Right.
are doing that. So yeah, I mean, so it seems like you shouldn't be so heavily overlapping.
Yeah, I haven't thought about redshift space distortion. So this is work in preparation. So one of the things I showed was this second-order kernel. So the kernel that relates two linear density fields to the second-order density field. Okay, and if you look in your favorite review on perturbation theory, somewhere in equation 137, 138, you'll find this kernel and the same kernel for the velocities. You will also find in the section on Lagrangian perturbation theory that, so this is the Zeldovich displacement field. This displacement field relates some fictitious Lagrangian coordinate to the actual position of particles, and its divergence is minus the density field to first order, and then to second order you have a relationship between this and the first order displacement field. Now these formulae do not account for several effects. First, they assume that the universe is matter dominated only. And they always say, oh, if you account for omega m is not 1, then you get some correction at omega m to the minus or to the plus some very small power law. But this is always by when they take a universe with cosmological constants or curvature, but not radiation. So a redshift 100, radiation contributes 3% of the background density. And so if you account for this not only in the linear growth, but also in the second order growth, you change your kernel, and you will have some redshift dependent coefficients, which I'm showing here. And you see that at redshift 100, some of them are like 5-6%. So in the era of percent level, large-scale structure, you would really want to get your initial conditions better than 6%, which is currently, this is the inaccuracy. Well, it's the inaccuracy of the second order part of the initial conditions. Second assumption is that the dark matter is cold and has been cold forever. Baryons, as we know, make up 17% of the total matter. And they are cold after redshift 1000, effectively, on all scales larger than their gene scale. But they only become cold at redshift 1000. And so there is some transient. It takes some time for them to catch up with the dark matter. And so at redshift 1000, you have an error for the baryon fraction to these kernels, which is, again, 17%. And then this error decays. But at redshift 100, which is the redshift at which you start the n-body simulations, you still have a couple percent error for not accounting for this. Third assumption is that the matter is a fluid, again, after recombination. But the total matter is not a fluid because it's made of baryons and cold dark matter, and they have a relative velocity. So by definition, you don't have a single flow, but you have a two-flow system. So the total matter has actually a non-vanishing stress tensor in the momentum equation. So this again changes this coefficient of the bispectrum. So this change is because of the initial conditions by saying the velocity of the matter is not that of the cold dark matter only, but it's also that of the baryons. And this is when you count, so this is, again, a few percent at redshift 100. And this is about percent-ish. It's when you account for this non-zero stress tensor. So you say, my matter is not a fluid. I put in a stress tensor, and I get some effect on the coefficients. Okay. So this is still in preparation, but should be out soon. Right, that was quick.
Yeah, so can you go back to the F with the displacements?
Yes, right. So what I didn't say is that so this will also be modified with coefficients, and you can see that they're related because there's a 7 here and here too. And then, but there will be, I had like alpha, beta, gamma, and then there will be some different combinations of alpha, beta, gamma, and actually there will be another term here. Okay, part 2. How can we constrain dark matter interactions with standard model particles? So I'll talk about two things. One is with 21 centimeter with Julian, Munoz, Eli Kovets, work in preparation. And the second one is a recent paper with me, Jens Kluba, and Marka Mankowski. So currently what are the methods to try and detect interactions of the dark matter with standard model particles? First thing would be direct detection constraints. So you've probably seen plots like this. For example, this is from the Xenon 100 collaboration. So this is the constraint on the WIMP nucleon cross-section in centimeters squared as a function of the WIMP mass. And what you see here is that around a few GeV of the WIMP mass, the constraint goes to infinity. Basically, the reason is that the dark matter needs to be heavy enough to give a recoil to the nucleon in the target. So you can only constrain masses with more than a few GeVs of mass. Here, these are constraints on the dark matter electron interactions. And the way it works is that dark matter could ionize electrons from the target medium. And so again, now it takes only a few MeV to ionize an electron. And so you hit a wall now, not at a few GeV, but at a few MeV. And so you cannot constrain the cross-section below these masses. So it would be nice to have other, in any case, complementary constraints in mass range and in different probes too. So if dark matter interacts with baryons, of course it will have some cosmological effects. First effect is that they will exchange momentum. So you will modify the fluid equations. So this is the fluid equation for the baryons, has the gravitational force, the coupling with the photons through Thomson scattering, which will make, before recombination, the baryons want to have the same velocity as the photons. And if you have scattering with dark matter, we'll have a coupling of the dark matter and the baryonic velocities. So it will want to make them have the same velocities. And the same happens in the dark matter equations. So this effect is used already to set constraints on the cross-section from either CMB anisotropies or large-scale structure. So there are several papers that give some constraints. There's also another effect, which is what I will focus on, which is the heat exchange. So again, if you couple baryons and cold dark matter, they will want to have the same temperature. So this is the evolution equation for the baryon temperature. There's a term that couples it to the photon temperature through Thomson scattering again. So this is what maintains the two temperatures equal up to redshift 100 or so. And then now you would have a new term which would couple. So the dark matter would now become warm. It would have some temperature. It would get coupled to that of the baryons. And same thing for the dark matter temperature. So let me first. So of course, so this can have an effect on the 21 centimeter spin temperature because it depends on the gas temperature. This was already pointed out by this work, recent work, Tashiro et al. But we're adding something which actually is really important for the effect. So what was neglected before is that it was assumed that there's no bulk flows between baryons and cold dark matter. Now, if you have, so we know that there are relative velocities between baryons and cold dark matter, and actually this relative velocity is supersonic after recombination. It's like Mach 5 or something. So the kinetic energy in the relative velocity is actually larger than the thermal energy of the baryons. And so if you have these dark matter and baryons that collide, you could transfer this bulk flow into into heat. Okay, and so what you conserve is the thermal energy of the dark matter and the baryons and the bulk kinetic energy. All right. So even when the baryons and the cold dark matter have the same temperature, if they have a bulk flow, you will heat up the baryons, and you will heat up the cold dark matter. So the equation I wrote before, you have the usual photon coupling term. You have this coupling term that couples the two temperatures that try to make them close to one another. Here, this will depend on the local relative velocity between the baryons and the cold dark matter, if the cross-section is velocity dependent. And you have an additional term which is strictly positive and depends on the bulk flow. All right, and same thing for T gamma. So this means that the gas temperature and as a consequence the spin temperature and as a consequence the brightness temperature of 21 centimeter will become functions of the local relative velocity between baryons and cold dark matter. And the relative velocity of baryon cold dark matter fluctuates on large scales. As we know since, well, it was pointed out by Celiakovic and Hirata. I mean, it was known, you could get it from the Boltzmann codes, and it was pointed out that it has an effect on small scale power. Right. And let me explain what this leads to. So we have considered so far, because this is still work in progress, cross sections that go as v to the -4. And the reason is that these will have the largest effect on 21 centimeter, while not necessarily affecting so much the CMB. Because as the coupling becomes larger as the temperature drops, as the velocities and the temperature drops in this case. Okay, so this is, such cross-section would happen, for example, for a milli-charged dark matter, but for also other models. So here I am showing, this is from a plot from Julian, this is as a function of redshift, the brightness temperature, because you can't see. The black line is the standard scenario. So the brightness temperature is 0 at high redshift because...
Does it saturate somewhere, this cross-section? I mean...
Does it saturate somewhere?
I mean, like at some low velocity.
Oh, you mean does it go like as to infinity as v goes to 0? Yeah, right. I'm sure there is some limit, yes, but I don't know exactly.
So it's not based off of some actual model, this is just some...
Yeah, here is parameterized, but you can find many models that give you something like this. I don't know at what velocity they stop.
So the Sommerfeld enhancement is something similar as this?
I wouldn't know. I don't know. I mean, this is, if you really take two charges, this is the cross-section again. You just say, I have two charges. The potential is proportional to 1 over r. And so the deflection will be at a radius such that, so r0 is such that the kinetic energy is v of r. So you get that r is proportional to 1 over v squared. The characteristic radius at which, and so then you get the cross section, which is proportional to r squared, proportional to 1 over v to the 4th. So this is a Sommerfeld, well, it's like an enhancement, it's a focusing enhancement. Yeah. But I don't know what's the limit of, at low velocities. Yeah.
Yes, I guess that once the cross-section becomes like comparable to or something.
Sorry?
I guess that one's like the, comfortability wavelength, I guess, comparable to this.
Exactly. There might be some mass, depending on the mass of whatever is causing the interaction and stuff like that. It's a phenomenological model. Let's see. So yes, the brightness temperature at high redshift, the gas and the CMB temperatures are the same, basically, are very close to one another. So the spin temperature, which can only be between these two, is very close to the CMB temperature, so the brightness temperature is 0. At low redshift, the gas temperature cools down faster than the CMB temperature, and collision maintain the spin temperature equal to the gas temperature, so you have an enhancement, a negative enhancement of the brightness temperature. And finally, at low enough redshift, the collisions become too inefficient, and the spin temperature recouples to the CMB temperature. Okay, so this is the standard story for 21 centimeter brightness temperature. Now, if we look at the blue curve, this is if we have no bulk flows, and we have this parameter here, sigma 17, the normalization of the cross-section equals to 1. And by the way, the limits currently from the CMB are this parameter has to be less than 2-ish. So if it's equal to 1, what happens? I wrote it down so I can explain it even if I forget. So yes, so because now you have the gas is coupled to the cold dark matter, so the photons, which were trying to maintain the gas as hot as them, they now have to maintain not only the gas but also the cold dark matter. So it takes more, so they're less efficient at maintaining the whole gas plus dark matter at sufficient temperature. So the gas temperature is smaller, which is why you get a bigger negative brightness temperature. But at low redshifts, because the collisions are increased with the temperature, so at low redshift, collisions become inefficient more quickly, earlier on, because the temperature is now, the gas temperature is lower. So the spin temperature recouples to the CMB temperature earlier on, which is why these curves cross. Now, if we look at the red curve or the purple curve, this is when we count for relative velocities, and you see that they are higher. So the gas temperature is closer to the CMB temperature. And this is because the bulk flows are now dissipating into heat, and they're heating up the plasma.
So that goes into my question of why is F strictly positive? Why can't it go the other way?
Why is F strictly positive?
With cold dark matter, there's no energy in the dark matter, so it goes from the baryons into the dark matter.
Yes.
And it's warmer. But with the flows.
Yes.
Why can't you have energy going from the baryons into the dark matter? Why does it go one way?
Well, so it's more of a bulk flow, bulk motion. So let's go to the center mass frame, right, which doesn't change. So this bulk motion transforms into heat for both baryons and the dark matter, for both.
Oh, okay, got it.
Right. But we only, but it's a net heat for both of them.
Right.
And it will be shared differently depending on their masses, but it's a net heat for both of them. And all this depends on the mass. So now between this curve where 0 relative velocity and this curve, so this is with a 1 sigma relative velocity, this purple curve. So at each, if you look at different patches, each patch will have a different value of the relative velocity. And so the spin temperature, hence the brightness temperature, will fluctuate by as much. So the fact that the spin temperature depends on the local bulk flow, and that this bulk flow fluctuates, will give you a large fluctuation of the signal. So we will not only, so this is the mean brightness temperature, and what this is doing is it's not only affecting the fluctuations, but also directly, in a sense, affecting the mean, the local mean brightness, and can make it fluctuate by a large fraction. So this is for the sigma 17 parameter of 1, like in this plot. This is the power spectrum of 21 centimeter, the standard power spectrum, and these curves correspond to the power spectrum. I don't remember, I think it's at redshift 30 for mass of the dark matter, either of 1 GeV or of 0.1 GeV or of 10 GeV. Okay? And so you can see that even for this parameter, which is smaller than what's currently excluded by the CMB, you can have a significant enhancement in 21 centimeter. So these are some estimates. So because we have Eli Kovets with us on this paper, and he actually, put in real realistic noise in the instrument. So these are more realistic than what I said for the bispectrum. So this is the minimum cross-section that would be detectable by a realistic SKA-like experiment that would have a baseline of 6 kilometers. So would observe the sky up to a multiple of 6,000 and for 5 years with a covering fraction of 0.02. Eli said it was realistic. I don't know. Maybe Richard. This would be a redshift 20 to 30.
Obviously, at those kind of redshifts, it seems that you're starting to get all the astrophysical stuff hitting you. So
yes.
the Root field effect is like
yes, I agree.
starting to drive the temperature back down.
I agree. Yes. So it's not so clear, so clean after 30. Yeah, I completely agree.
Is it really undetectable at higher redshifts?
So I think that's a good question, and I don't know. We haven't checked that. If you go beyond 30, you don't get much because the noise increases so steeply. Because of the synchrotron. But so yeah, it's not clear how much you lose if you stop at 30 instead of stopping at 20. But it's probably a lot. And this is optimistic. It's still not cosmic variance limited as we did in the first paper. But this is if you have now a baseline of 50 kilometers and you have 10% covering fraction, so you have, I don't know how many antennas it would correspond to. You observe for 10 years. Then you could constrain this parameter basically to 3 orders of magnitude better than the CMB. So 21 centimeter could measure baryon dark matter cross sections much better than the CMB does. That's the bottom line. Okay, last part of the talk, I will discuss the effect of this on spectral distortions. And this is the part that I find most interesting, so please wake up if you fell asleep. So this is a black body spectrum. Okay, that you all know and love, and we know that the CMB is the best black body spectrum ever measured. Phi-RS measured it to be a black body to within 50 parts in a million, and some of the people on the Phi-RS team are now proposing PIXI, which will measure in principle the CMB spectrum to an unprecedented accuracy of 10 to the minus 8. Okay, so there's a whole new frontier that we could explore here. So why is the spectrum interesting? Because it can tell you about the early energy injection, the early thermal history of the universe. So if you inject energy or remove, as we will see, from the plasma at redshifts bigger than 2 millions, then this energy will thermalize. The processes creating and destroying photons are very efficient at these redshifts. So you will just thermalize this energy and you will just change the temperature, but it will remain a black body. If you inject energy between redshift 50,000 and 2 million, then you cannot create and destroy photons very efficiently at these redshifts. However, you can change their frequencies through Thomson scattering very efficiently. So the spectrum will reach an equilibrium. However, it's an equilibrium at constant number of particles, and this is a chemical potential type distortion. So you will have a Bose-Einstein distribution with a chemical potential. And finally, if you inject energy in the plasma at redshift less than 50,000, then even the redistribution frequency is not efficient anymore, and you get a distortion which is exactly like the Sunyaev-Zeldovich effect, except that you don't have a very hot cluster. You have whatever small, tiny difference of temperature between the photons and the electrons, and this is called a white type distortion. Okay. This was worked out by Hu and Silk a while ago, and then Jens Kluba and the collaborators have tons of papers on this, if you want to read. So what kind of energy injection mechanisms are there? So in the standard vanilla universe, there are fluctuations on all scales, power law fluctuations on all scales, and these fluctuations dissipate because of Silk damping. So this dissipation of acoustic waves go into heat. And so this gives you in the standard, if you just extrapolate what is measured from the CMB for the power law spectrum, is something like 10 to the minus 9-ish distortion to the CMB. So it would not be observable even with PIXI. If you have an annihilating or decaying dark matter particle, or if you have primordial magnetic fields, or whatever crazy scenario you can come up with to inject energy into the CMB, you would get some distortion. Okay, so, which is why it's interesting, because you could measure all these things. Now, another process which is somewhat slightly less intuitive is how can you extract energy from the photons? Okay, so all the other processes where, if you heat up the electrons, like the Sunyaev-Zeldovich effect, then the photons will gain some energy from the electrons. Now, how can you extract energy from the photons? So if the baryons were left alone, they would just want to cool down adiabatically. And because then when they're non-relativistic, their temperature would go as a scale factor to the -2. So the derivative with respect to time is just -2 times Hubble times temperature. However, baryons are not left alone. They are constantly scattering. Free electrons are constantly scattering with photons, and then the free electrons are scattering with protons and helium nuclei and sharing their energy with them. And so Thomson scattering maintains the temperature of the baryons equal to very, very good accuracy to that of the CMB. And this is true all the way down to redshifts of about 200 or so. At what point we start being able to observe 21 centimeter signal. So here we're concerned with redshifts of 10,000 and beyond. So this is true to very high accuracy. So the baryon temperature, in fact, goes as a to the -1. So this derivative goes as -h times baryon. So the difference between these two is the heating rate. Okay, so you have to inject delta TB dot equals to plus h times T baryon. So the net heat flow from the CMB to the baryons is 3/2 of the number of baryon times the difference between these two things, which is h times TB. And so this heat flow goes into the photons. So the net heating rate of the photons, so this is the energy density of the photons, and all these scale factors are just to say that this thing would decrease as 8 to the -4 in an expanding universe. And so this heating term, or this cooling term for the photons, goes beyond the adiabatic expansion of the universe. If you put this on the other side, you use the fact that rho gamma goes as 8 to the -4, and then you plug in that the energy density of photons is roughly 2.7 times their temperature times their number density. So it's not 3/2 like for non-relativistic, but it's some number. Then at the end of the day, you get that the distortion, so the change in the energy density of the photons, the fractional change, is the ratio in number of baryons to photons times the integral of h dt, which is just some logarithm. Okay? So these scale factors, what are they? So the minimum scale factor is the one corresponding to redshift of 2 million, the time at which energy injection actually goes into distorting the plasma. Otherwise, it would just change the temperature. And the maximum scale factor is, well, it could be redshift 200 if you're interested in the total distortion. So redshift 200 is the time when this does not hold true anymore, okay, where this starts to hold true. Or if you're, say, interested only in the mu type distortions, then it would be a redshift of 50,000. All right? So one of the main points here is that this distortion is proportional to the ratio in number of baryons to photons times some log, and this number is just 10 minus 10 in the standard universe. So this extraction process, which happens in the standard universe, it distorts the CMB by 10 minus 9 or so. Okay, again, unobservable. So now let's add dark matter scattering, either of photons or of baryons, to the mix. So first of all, this only works if dark matter is non-relativistic. If it were relativistic, then its temperature would decay as 1 over the scale factor, regardless of what it does to the photons. Okay, so it has to be non-relativistic. It has to want to cool down faster than the photons would do. So this limits us to masses heavier than a keV or so. So if the dark matter scatters off photons, the exact same effect that I just described holds. Okay, so you will have a distortion that's proportional to the ratio in number of dark matter particles to photons. If it scatters off nuclei or electrons, then it becomes thermally coupled to the CMB, but indirectly. And the process is that, well, Thomson scattering takes energy from the photons to the electrons, and then electrons scatter off protons and scatter off helium nuclei, and then either electrons or nuclei will scatter off dark matter particles and share this energy with them. Okay, so now there's a bigger heat bath that can absorb the energy of the photons. So every photon bit of energy taken from the photons is shared among more particles, and so it takes more effort from the CMB to maintain everything in equilibrium. All right. So in both cases, the distortion to the CMB is some number times the number density of dark matter particles divided by the number density of the photons times, again, this log. The minimum scale factor is the same as before, it corresponds to redshift 2 million. And the maximum scale factor is, again, the time at which the dark matter is no longer thermally coupled to either the photons or to the electrons and baryons. So it's the decoupling time. And this time depends on the cross-section. So the information on the cross-section comes through the decoupling time. And this ratio depends, because we know the density in mass of the dark matter, the mass density, so then this will be inversely proportional to the mass of the dark matter. So this process is more efficient as to probe light dark matter particles. Here I'm showing the absolute value of the photon distortion for a velocity-independent scattering with nuclei, but we studied general parallel dependencies in the paper as a function of the cross-section. So first of all, what you see is that the higher the dark matter mass, the smaller the distortion is, accounting which comes from the fact that it's proportional to the number density of dark matter particles. And also what you see is that all these curves plateau at high enough cross-sections, and this is when the decoupling time is basically all the way to redshift 0. We didn't really take it to redshift 0, we took it to redshift 10 to the 4, so we're only interested in mu-type distortions, but that's basically the maximum you can get. And so now if we look at phi-ras can not say anything about dark matter masses, dark matter particles whose mass is more than about 0.2 MeV. Okay, but if we had, so I didn't plot it on this curve, but we can understand from the Pixie. So if you for Pixie, this limit is about 1 GeV. So heavier dark matter particles will not do anything that could be detectable by Pixie.
So for baryon, what was the equivalent number again?
So for baryons, the distortion is 10 minus 9, and so you have at 1 GeV, you have like 5 times more dark matter than baryons, which is why you get 10 minus 8. So if you look at a 60 MeV curve here, by saying that the distortion, if Pixie was able to observe, well, when Pixie hopefully will observe these distortions, and if it doesn't see anything, it will tell us something about the cross-section not being larger than some number. Okay, so that's the idea. So this is the final and money plot. So again, this is for velocity and energy independent cross-sections, but you can plot the same thing for your favorite dependence, velocity dependence or energy dependence of the cross-section. The solid lines are the constraints that exist now, that we have set now with already phi-ras data. Okay? On either the photon baryon cross-section or the photon dark matter cross-section, electron dark matter, or proton dark matter. So as I said before, direct detection experiments do not probe at all the dark matter nucleus interaction for masses less than a few GeV. So they would be somewhere here on this plot. The dark matter electron interaction is being probed, and it's significantly lower, better cross-section than what we get here. However, it stops at masses of a few MeV. So this direct detection experiment do not say anything about this whole region of space. And the photon dark matter cross-section is constrained, I found this paper, I think it's Céline Bohème and collaborators, so if you had interactions between photons and dark matter, you would cut off the small scale power spectrum in the dark matter, and then you would have less Milky Way satellites. And so they ran simulations and counted the satellites and compared with the data. And so then they can set some limits. So yeah, these are the existing constraints, and this is how you could extend them with a Pixie type experiment all the way to a mass of about a GeV. So yeah, that's the conclusion. You could constrain the interaction between dark matter and baryons or photons at redshifts 1 million by looking at the spectral distortions of the CMB. You can actually already do it, and you can do it better with better experiments. That's all.
So for the relative velocity, where you had the coupling to the dark matter and so on, what temperature does the dark matter attain in that case?
I think for the maximum limit that we will have, it never really reaches the baryon temperature.
But if it did, that would be a big deal, right? Because that would change the.
I don't think it would be a big deal because it's not a big deal for baryons on scales on wave numbers less than 300 inverse megaparsecs.
Well, there's a Jeans mass in the NPM
Right.
for baryons that sort of controls the small scale structures.
Yeah, exactly, but it's at very, very small scales.
In terms of 4 solar mass.
Exactly, yeah. So it would maybe control structure, but at very, very small masses. But the point is that the temperature never reaches the baryons. But maybe someone was going to ask this question, I said before. So that means that treating the dark matter as having a temperature is not correct. Because if it interacts weakly, it will have some velocity distribution, but there's no reason why it should be Maxwellian. So all these equations are basically taking temperature as some measure of the velocity dispersion of the dark matter, but so they should be accurate to order 1, but not sub% accuracy.
Anyone else?
With these spectral distortion measurements, you can, if you actually do this experimentally, you can only really pull out a few numbers describing the distortion. Like how limited are you in terms of disentangling something like this from all the other effects that are going on, like damping of acoustic waves?
Well, I mean, damping of acoustic waves, I guess if you have a very unusual small-scale power spectrum, you could have something. That's a very good point, and I don't think you could, if you had a super-duper spectral distortion measurement, Jens would probably tell you that you can measure more than a few numbers.
Right.
But if you can only measure a few numbers, yes, then what is creating this distortion is very difficult.
I guess it's not, I remember talking again about this, it's not that you can only measure a few shapes of distortion, it's just that anything you ever do gets plowed into only a few modes of distortion.
Well,
why was it slightly unusual?
I don't think it's quite. I think so. If you do things at high redshift, more than 50,000, it's a mu. If it's less than 10,000, it's a y. If you do something in between, then it's something that is in between, and it's a continuous change. So there's an infinite number of shapes in principle. But if you have some rather smooth function that you extract, you're going to project it onto mu, onto y, and then what's left is smaller and smaller. But what I would say for this, however, is that this is a perhaps more unique signature because it's a negative mu distortion and a negative y distortion. Whereas all the other effects are injection of energy. This is an extraction of energy. So this could be more of a unique signature in this sense. No, it just inverts the shape of the distortion. So
if you had something generating if you came up with a very result near zero, say,
right,
then it doesn't actually place a limit because you could have energy.
You could have several tooth fairies at the same time. Yes.
So many tooth fairies, right?
Yeah.
Occam's razor means there shouldn't be making up like 10 different counterpoints.
That's true. There are some things you expect to be. There are some things that inject energy you do expect to be there.
Right. They're all at a level.
But they're smaller. 10⁻⁹ you expect normally. But though the small scale, the acoustic waves you cannot tell because it depends on very, very small scale modes, which you don't measure. But if the small scale power spectrum doesn't do something too crazy, then you expect it to be small.
If you had a dark matter candidate which had some small annihilation cross-section and had some scattering cross-section, then you would inject and extract energy at the same time.
Yeah, absolutely, yeah.
So are the K-modes, damping leads to the injection of power?
Sorry, can I say again?
So which are the wave numbers
that lead to injection of power?
Injection?
Jens had a paper on this, and it's like K to 10 to the 20 or something. I mean, it's just...
No, 10 to the 20.
Yeah, we'll look it up. But I remember he had some constraint on the very small scale power at K to the 20
so
because of this dissipation.
Sort of coupling between the dark matter and modes would be gone anyway because of the temperature of the dark matter.
I see.
So actually, yeah. So well, yeah, so these canceling two theories, I guess, can't happen to some extent because this effect should kill the other effect.
Wait, why would they be gone anyway? Because the photons completely dominate the energy budget.
Oh,
so.
yeah, sorry, yeah, that's right. It's damping the photon mode, it's not the.
Right.
All right, let's stop here.
But
I think